let's go over graphing rational functions. And a rational function is the idea of a polynomial. So let's say the numerator of this fraction is a polynomial divided by another polynomial. So rational functions are essentially polynomials divided by polynomials. That's what they mean. Okay. And let's talk about when we're going to make a sketch, a graph. What are our major things that we're going to need? We're going to need the x-intercepts. We'll need the y-intercepts. Because it's a rational function, and I never spelled this right. Do you have it written somewhere? Asymptotes. That's Y-M-P-T-O-T-E-S? All right, thanks. And the asymptotes, y-intercept, x-intercept, asymptotes, and those are essentially the main things we got to cover here, okay? So, the easiest thing, well, I shouldn't say the easiest thing. First thing we'll do is we'll figure out what the x-intercepts are. It's definitely not the easiest thing, okay? And x-intercepts are when the y value of a function is equal to 0. Okay, so let's keep that in mind. So when y equals 0 is when we have x-intercepts. Okay, so I want you to look at this as just a fraction. Okay, for a fraction to equal 0, do you know which or what kind of has to happen with the fraction? There has to be a division by a number of 0. So there has to be a 0 somewhere. Do you know if it's in the bottom or the top? Unsure? That's okay. If you put it on the bottom, it's an undefined function. And that's how we get asymptotes, things that are undefined. So if there's a 0 on the bottom, that's where we get asymptotes. So that's how we figure out what an asymptote is. When the top, just the top here, is equal to 0, that's how we find, sorry, I didn't mean to do that, x-intercepts. So I'm going to kind of reset this up. We're just going to focus on the numerator of this rational function, okay? And it's set equal to f of x. And f of x is essentially the idea of y. Okay, so let's scroll down. Let's say y is equal to, I forget what it was, x minus 1, x minus 1, x plus 8, right? And we just said when y is equal to 0, so we're going to replace y with 0. Okay, and we get x minus 1, x plus 8. And in order to be equal to 0, because we're multiplying essentially two terms, one of these terms must be 0. So we're going to end up with two answers. We're going to set both sets of brackets equal to 0. So we have 0 is equal to x minus 1, and 0 is equal to x plus 8. Oh, let me get the baby here. Baby's still crying. But we can still set it equal to 0. So let's move the negative 1 over, so that becomes just 1, right? And we move the 8 over, it becomes negative 8. So you get x is equal to negative 8. And x is equal to 1. So our x-intercepts are at negative 8 and 1. So let's say we're doing a rough sketch here. Okay, one of the x-intercepts is at negative 8. Another one is at the value of 1. So we know it's crossing there, but we got to kind of figure out where it's going from. Okay, some other information that will help us is the y-intercept. Okay, let's do the y-intercept in highlighter green. Yes. Y-intercept. How do we find the y-intercept? Well, the y-intercept is when the x values are equal to 0. Okay. So for the y-intercept, we're actually going to take the entire function here. Okay. So I'm can I highlight it over? Yes, I can. Oh, I chose this color as well. So we're going to take the whole function here. Okay. And we're just going to plug 0 in for x and see what we get. Okay. So let's scroll down a little. Should maybe try to. This was for the x-inter, so we know what we did. This is for the y-inter. Terrible handwriting. So f at x or y, it doesn't really matter. And actually, it's not going to be f at x, it's going to be f at 0. We know we want to substitute 0 in for the x value, right? So we're going to solve f at 0, and that will be a y-intercept. So x minus 1, x plus 8. So we have 0 minus 1, we replace the x. 0 plus 8, remember that was the numerator of the rational function from above. And then I think it's x plus 8, so 0 plus 8, and plus 12 or minus 12? Minus 12. So 0 minus 12. So all we did was replace all the x values with 0. That makes sense? Okay. So we get negative 1 times 8 over 8 times negative 12. Could be tough with all the multiplication, but what's really nice is I have two 8s. These cancel out. So I'm left with negative 1 over negative 12, which is 1/12. So the y-intercept Ooh, I went up too fast. There we go. The y-intercept is at 1/12, which is probably there if, let's say that was 1. That's where the y-intercept is. So we cross over at that point. Okay. And finally, the very important part of this here are our asymptotes. Now, asymptotes. We're going to figure out, oh my god, we're going to figure out the vertical asymptotes to start. Okay, so the vertical asymptotes, and let's see if I chose good highlighter colors. Can I do that? No. And I think this will turn it black. Yeah, we won't be able to see. Okay, that's okay. Let's just use a color. We're going to focus on just the bottom part of this, okay? And we're going to set that equal to 0. And the reason being is essentially it cannot be set equal to 0, because if it is, we have an undefined, it would be, oops, undefined if it's equal to 0. I know it's not great writing. So x plus 8, x minus 12. So let's go down to here. ASYP, so our asymptotes here. We have our x plus minus 8, x minus 12. Did I say those right? Plus 8, okay. Plus 8 minus 12. Okay, and think of it as it cannot equal 0. Okay, so I'll even put that symbol in there so it's obvious for us. Exact same thing as we did with the numerator to find x-intercepts. We set both bracket equal to 0, or we set it not equal to 0, I should say. So x plus 8 cannot equal 0. X minus 12 cannot equal 0. Okay, which means x cannot equal negative 8, and x cannot equal positive 12. Okay, so here are our asymptotes. So if we were to graph this again, we have a vertical asymptote. It looks like we have a vertical asymptote right where we said we had an x-intercept. So what does that mean to us? One was that negative 8. What was the other one? Positive 12. So that's probably like way out here. Okay. So what does that mean to us? Well, let's go take a look here. So we have an x-intercept, so we said, and a vertical asymptote in the same spot. So this begs a question, because if you have a vertical asymptote, you can have an x-intercept. Essentially, the function never hits there. Right? There we go. So what's happening? So we got to take a look at this, and this is where this idea is happening. We have, maybe I should do it at the very top. We have a numerator and a denominator that essentially cancel each other out. Okay. So whatever value makes both of these the value of 0. So let's say f at negative 8. So if I had plugged in negative 8 here, this bracket here would be 0. This bracket here would be 0. 0 times anything becomes 0. So if f at negative 8 is 0 over 0, this is also an undefined one. But because it's 0 divided by 0, it's a special relationship. It's creating somewhere a hole in the function. Okay. So what that means is instead of the function kind of going along the vertical asymptotes, kind of like these would, they do something like this maybe, something like this. Who knows what type of function? We haven't really got to it yet, right? But what's actually happening is it's going to, for this vertical asymptote, yeah, at 12, it's definitely not going to touch. But here it's going to continue at it. There'll be a hole in the function, and then it'll continue on its way. It won't make a turn, okay, like it normally does. So if you ever have an x-intercept and a vertical asymptote, be aware that when you're graphing it, it's actually going to approach it at some value, be just a hole there, and continue. It won't turn like it normally does on the other asymptotes. Okay. Okay, so we've got that. We have a vertical asymptote at 12. We have a vertical asymptote at 12. And what else do we need to know for graphing? A horizontal asymptote we should talk about. Okay, horizontal asymptotes. So we need to know if the highest power of the variables on the numerator and denominator are the same, or essentially we have to know what they are. So one way to do this is to expand the entire function. So we can quickly do this if we need to at the bottom here. I'll quickly go into it. So f at x is equal to x minus 1, x plus 8. I'm going to do this part quickly because I'm going to assume you're already good with FOIL. X plus 8, x minus 12. Okay. So x times x gives us x squared. X times positive 8 is plus x8, so that becomes 7x. So I'm doing the math all together in just one step here. And this becomes x squared, negative 4x, and negative 6, carry the 196. Okay, what's key here is the highest powered exponents, and essentially their coefficients. Okay? In this case, they are equal, right? These two are equal, so we do have a horizontal asymptote. If the numerator power, okay, so I'm going to say xn, I'll call this n in the bottom one xm, okay? So if this is xm and this is xm, if n is greater than n, excuse me, there is no horizontal. If m is greater than or equal to n, yes, there is a horizontal. Come on, catch up. There we go. Chicken scratch. But does that idea make sense? If the numerator is larger than the denominator's power, then there's no horizontal asymptote. It ends up being something kind of different, like an oblique or a...
Aren't they the same?
No, this is where the denominator is greater than or equal to. And yeah, see where they're equal to? If they are equal to, there will be a horizontal asymptote. And how do we know what it is? There's a whole bunch of things I can show you with infinities and stuff, but if they're equal, which they are in this case, we just divide the numerators. And the numerators are 1 and 1. So what's 1 divided by 1 here? It's equal to 1. So you have a horizontal asymptote at y equals 1. So if I scroll back up again, remember I kind of drew in 1 there. We have a horizontal asymptote, put in red, at the value of 1. Okay, so and this whole, I didn't quite decide where it is. I actually think it's probably lower down or something like that. The last thing we kind of had to figure out is how this function is going to look when it's graphed. So overall, this is a positive function. So what do positive functions look like for rationals? Well, if it's positive, we kind of think of it as something like this. Okay, if this is a positive type function. If it's overall a negative type function, we'll just do that in blue. It would be kind of the opposite. It has that look. And one way you can remember this is if it's just, think of a slope of a linear function, slope would cut right through it if it was positive. And if we had a negative slope, the slope would cut right through this one, like that. So you can kind of tie it to what you know with linear functions, okay, as a way to memorize that information. So because we know it's kind of in that style that I've drawn in black as a positive function, when we go our rough sketch here, this is essentially where the two horizontal asymptotes meet. Remember we said that this is not a vertical asymptote anymore. Delete. I know I said horizontal asymptotes meet. That's where the vertical and horizontal meet. This one's now a hole. So this is where our x, remember if it's positive, it does something around here. And then it does another something around here where it crosses at 1. We know that's one x-intercept, y-intercept here. There's a hole here. And then it continues and just never touches that. So I know I didn't leave us a lot of space on the side. But we can get a better look at it over here. Zoom out just a little. Okay, and here's our function where y is equal to 1. Okay, you'll see that we have a horizontal asymptote. Where x is equal to 12. Turn it on. Color blue. That's where our vertical asymptote is. And the coordinate at 0, or sorry, not 0, at 8, on the function. Oh, went too fast. We're almost there. No, there was, can't get it. Hey, negative 8 is an undefined hole at that part of the function. Okay. So I named the function f at x. So you'll notice when I plug negative 8 in for x, it says it's undefined. So this is also a calculator, this program. Remember f at 0, this is where our y-intercept should be, equals 0.0833, which is 1 over 12, right? That's the exact same value, right? So that was where our y-intercept is. We said it would be there. And what was the other thing we wanted to find out? Was there anything else we plugged in? No, we just plugged in 0 and -8. So we have an undefined value, and that's the y-intercept. So you can like plug values in to this function. Like if we plugged 1 in, if I plugged 1 in, this would be 0 here, right? And we'd be divided by 0. So if I say f at 1, we get a value of 0. So it also works as a calculator, kind of, this program. Okay, so just keep that in mind, that -8, it's undefined, even though it's kind of hard to see that.